lecture, we're going to discuss how to interface our PIC microcontroller with an accelerometer. So let's remember from our sensors lecture just how an accelerometer works. You can think about it as a spring mass damper system, and that mass is either compressing or elongating a piezo crystal. So depending upon what angle you hold that accelerometer at, that mass could be pressing and squishing that piezo crystal, giving a different voltage reading out, or it could be elongating or just not compressing the piezo crystal so that you do have a voltage level coming out. So it's all based on the properties of the piezo crystal. And depending upon how you orient the accelerometer, depending upon how fast you move that accelerometer, you will see different compression of that piezo crystal. And so accelerometers are typically analog devices. Acceleration is an analog quantity. It's not just you're accelerating or you're not. There's a whole range of acceleration that could happen. Accelerometers also are often three-axis accelerometers. So when we're thinking about motion, we're not just thinking about movement along a single axis. You could move up and down. You could move left to right. You could move in really three different dimensions. And so you want to think about how you can measure the acceleration in all of those different dimensions. Acceleration is typically expressed in G's. You may hear people discuss the G forces that are involved in certain things like roller coaster rides or a shuttle launching, or let's say a race car or something like that. And so basically a G is a multiple of the acceleration due to gravity, which if you're in SI units is 9.8 meters per second squared. That would be 1 G. And so the analog output of the accelerometer corresponds to how many G's of acceleration are being experienced in each of the three axes. So one of the things we can do with an accelerometer is we can detect pose. That is how a device is oriented. We can figure out if something's right side up or upside down. This is what is used inside of your smartphones and your tablets to determine whether you are holding your phone portrait or landscape, so it can reorient the information on the screen, pictures, and those types of things. And it's all based upon the influence of gravity on the built-in accelerometer. And so what we can do is we can actually measure the different signals coming out of an accelerometer, and we can figure out how you have oriented different objects. So this is good to be used as a tilt sensor, although sometimes a gyroscope would be used in that case. But if we're simply trying to predict one of two orientations, portrait or landscape, an accelerometer is pretty good for that application. So here you see the different ways that we could orient our accelerometer, and I would ask you to pay particular attention to this dot right here. That's going to be effectively our origin that we may be thinking about. And so if you have an accelerometer oriented this way, then your influence is a 1G down gravity. So you have negative 1G. If you were to rotate this around 180, then you'd have positive 1G. And so that would be, gravity is still acting in the same direction, but now you've changed your sensor's position. Likewise, if you oriented it this way, that gravity would be in the y-axis, and depending upon whether your dot is at the top or the bottom, that's either a positive or a negative 1G. You can lay your accelerometer down like this, and in that case, gravity is acting in the z-axis. If you turn it this way or upside down, you have positive or negative 1G that way. This is if you just have the accelerometer sitting on a shelf or mounted to a device, and that device is not moving, it's not accelerating, it's just oriented that particular way. So that's how you can identify the orientation of tablet devices and those types of things, is based upon looking at your different axes. And so if you were trying to figure out, let's say this were your landscape orientation and this were your portrait orientation for an iPad or a smartphone, then what you might say is, oh, okay, I'm going to be looking for the x-axis signal, and if I have something other than pretty close to 0, I'm going to think I'm in this mode, and then if I have something other than that on the y-axis, then I'm going to think I'm in this mode, and I can reorient my graphics accordingly. So when you're using an accelerometer, you need to understand a few things. Just like any other device, you need to understand the voltage requirements of that device. So you don't want to send too much voltage. You don't want to improperly power that device. So you want to make sure you have enough voltage. In case of certain accelerometers, you may need a voltage regulator, and a voltage regulator is probably a good idea for this so that your power supply is consistent. So you want to make sure if you're running off of a battery that your accelerometer output is not going to change in response to that battery draining as that voltage level changes on the battery. A voltage regulator is a good idea so that you have a steady state voltage input. The number of G's that you're going to be measuring is also important to consider in terms of choosing an accelerometer. So if you're simply trying to choose an accelerometer to determine the orientation of a tablet, maybe a few G's is plenty. But if you're trying to measure the acceleration of a rocket ship or a car or something like that that may experience more than just 1 or 2 G's, you might need a different accelerometer. So depending upon how many G forces or the number of G's that you're going to measure, you're going to have to choose an accelerometer accordingly. So your application will really drive what you're trying to do. So if you're trying to measure ballistics and acceleration coming out of firearms or military weaponry and things like that, you might need something very different than if you're just trying to put this inside of a smartphone. In lab next week, you're going to be using the ADXL335. This is a 3-axis accelerometer, and it is set up for a range between plus and minus 3 G's, which is a pretty good range if we're just trying to detect the orientation of the accelerometer. It has some voltage requirements on it, so the input voltage has to be between 1.8 and 3.6 volts. And what we will use in class is actually mounted onto a little breakout board that I showed you in class today, and that breakout board has a 3-volt regulator built into it. So your input voltage will be a set 3 volts, and you can just power that board with VDD, which is 5 volts, and that regulator will step it on down to the 3 volts that accelerometer needs. So let's learn how these things work. If you have 0 G, that voltage output is going to be basically half of the input voltage. So for the 3 volt input voltage, it's going to be 1.5 volts nominally, but there is a tolerance of 10%, plus or minus 10%. So it could be up to 10% above, which would be 1.65 volts, or it could be 10% below, which would be 1.35 volts. And then the sensitivity is based on how many G's it's designed to measure. And so in this case, your typical sensitivity is going to be between 270 and 330 millivolts per G. The nominal is 300 millivolts per G. So because it can be off by up to 10%, on the low end it's going to be adding 270 or subtracting 270. On the high end, it's going to be adding or subtracting 330, depending upon whether your G's are in the positive or negative direction. So let's look at our expected output. At 1 G, that would be 1 times the sensitivity above the nominal. So our nominal output voltage should be 1.8. That is because 0 G is 1.5, and then we're adding 300 millivolts or 0.3 volts nominally because we have 1 G above. We would expect our output to be 1.8 volts. But because we know there are 10% tolerances on both our sensitivity and our nominal 0 G voltage, our minimum would go down to 1.62 volts. Well, how did we figure that out? Well, if you're looking for the minimum voltage, you want to start with the minimum voltage that would happen at 0 G, so that would be 1.35. And then if you're talking about adding, the smallest amount you could add would be 0.27 volts. So if you add 1.35 and 0.27 volts, you get on the low end here 1.62 volts. On the high end, if you're talking about adding the maximum voltage that you could have here, that would be 1.65 volts, and adding the maximum voltage that could come from your sensitivity, if it were on the high end, then you would have 1.65 plus 0.33. That would work out to this 1.98. You can do similar math to figure out the nominal at negative 1 G, your minimum and your maximum, and here you see your nominal at 2 G, your nominal at 3 G. And so in your in-class exercise for Friday, I will ask you to fill out a table that includes the rest of those values. There is another accelerometer. I happen to have a few of these. This is the ADXL326. It behaves in almost the exact same way, except it is designed to measure plus or minus 16G. And because it uses the same input voltage, what that means is its sensitivity is a lot less. So for 1G of acceleration here, you nominally only see 57 millivolts of change as opposed to the 300 millivolts of change that you saw before. And so with a 10% tolerance on that, here is our nominal range. And so in this case, because it's designed to measure much larger acceleration, one little G is not going to change the output voltage as much as it would with the 3G accelerometer. So in our lab, we're mostly going to be using the 3G accelerometer. I just wanted you to see this other accelerometer so you understand, if you had other technology, what scales. And so really what changes is your sensitivity per G. So how do you process the accelerometer signals? Well, because you're going to get an analog voltage out, you might have expected you're going to need to do an analog to digital conversion. And because you have three separate analog voltages coming out, one for the x-axis, one for the y-axis, one for the z-axis, you're actually going to have to perform analog to digital conversion 3 different times. And so we're going to need to pick 3 different analog pins to use for this particular lab. And let's remind ourselves of the 14 analog inputs we have available. We do have AN0 through AN3, which correspond to port A, bit 0 through 3. We have AN4, which is port A, bit 5. Remember, you skip one because there's an input voltage you can put in corresponding to RA4. And then analog 5 through 7 are up on port E, bit 0 through 2. And then you start getting into analog that is on port B. Now, in terms of what we are using, remember that we need some of those bits of port A to control our LCD. And in the lab, you're going to be putting some of your accelerometer information on the LCD. So we don't want to use the same analog pins that correspond to pins that we need to send information to the LCD. So what we're actually going to do is choose AN5 through 7 on RE0 through RE2 because we haven't used port E for anything else yet. So that's exactly what I said there. We're going to use RE0 through RE2 so that we don't conflict with the RA1 through 3 that you're going to need to drive the LCD. So how do we go about solving this problem? Well, what you're going to do is you're going to configure all of your analog ports and you're going to perform the conversion, and then after you do all of the conversion on all 3 of the axes, you're going to turn off the A to D. That's a good idea to do that because that will save some of your power. In the lab, that's not going to make that much of a difference because you're powering things based on your laptop's battery and you can always just plug that in. But it's good practice to get into saving energy whenever you can. So we're going to power down the A to D module, switch everything back over to all digital mode, and then perform the LCD operations. And then you're going to loop back, do the analog to digital conversion again, and then output the data that you receive onto the LCD. So here is basically our way we're going to go about this. We're going to turn off all of our interrupts. You could use an analog to digital interrupt here, but it's probably easier just to do polling because you're going to be changing channels, and the logic to handle this inside of the interrupt service routine will be a little bit more complicated. So it's probably easier just to go ahead and set up everything with no interrupts. We'll just do data polling. You're going to have to set up the appropriate channels as analog on ANCEL and ANCEL H, so you can look that up, make sure you've got the right bits going in there. Port E is going to be all inputs. That's going to be where we're going to do our analog input. So make sure in Tris E you set up all of those ports as inputs. D and A are going to be used for the outputs of the LCD, so make sure those are all outputs. And then you're going to need to configure ADCON 1. Remember, that's what sets your voltage limitations, and it also determines whether you're left or right justified. And then you're going to go through the LCD initialization that we've already talked about in terms of 2-line display and how your data runs in and clearing everything out, all those types of things. Then, outside of that configuration code, in an infinite loop, here's what you're going to do every time. You're going to use ADCON 0 to set up for the particular channel that you're going to be digitizing. You can just use the slowest conversion clock rate there is because The accelerometer is not changing all that fast. And then you need to enable the analog to digital conversion, but again, remember, we don't set the go until after we turn on the module and set up our channel, because we don't want it to go before we're fully configured for how we want it to run. Then we can just do some polling and wait on our go bit to go back low after the analog to digital conversion is done, and then you're going to want to store the result of that into an integer array. So I would recommend having an integer array that holds 3 different values, one for the x-axis, one for the y-axis, and one for the z-axis. Then you're going to, inside of that loop, after you store the first value, just continue and do the same thing for the y-axis channel, the z-axis channel. After you have all of those data collected, then you're going to power off the A to D module, switch back over into LCD mode, and just write out the information that's required in the lab, and wait 1 second so that you can actually see all the information on the LCD before you go back in and do the analog to digital conversion again. So, in terms of connection, the accelerometer board is going to require you to use VDD to power it and a ground reference, and then the 3 outputs will be connected to AN5, 6, and 7, which happen to be on port E bit 0, 1, and 2. And so you can easily just use the wires that come with your trainer kit to connect those particular pins. You don't need anything extra on the breadboard. You can simply use just 5 of the wires that came with your trainer kit.